Rolling without slipping is a special case. In fact, it's pretty much, we're never going to talk about rolling when you're not, or where there is some slipping. It's a special case. So rolling is a combination of rotation and translation. For an object that rolls without slipping, the translation of the center of mass is related to the angular velocity. So by no slipping, we mean that between the disk and the ground, there is no relative motion. And so in this kind of motion, we have a very special relationship between the velocity of the center of mass and the angular velocity. So the velocity of the center of mass is the velocity that the center of the disk is traveling at, all right, represented by this green arrow. And omega is the angular velocity of the disk's rotation. And so this is the viewer equation. We've used this before, and this is the relationship between these. And we want to convince you that this is true. And so in this first picture, we're following one part of this disk through one rotation, okay, as it goes around one rotation. And so here the little picture is showing you sort of 3 different pictures of this disk. Here are the little blue dots at the top, and it comes back down to the bottom. So the wheel has done one complete revolution. And so what that means is the distance that it's traveled is 2 pi r. Hopefully that makes sense. That's the circumference, and so as the wheel just rolls once completely, the actual distance that's traveled is 2 pi r. And we take this now and say, okay, so that x distance the center of mass has traveled is equal to the velocity of the center of mass times the time, and that's going to equal 2 pi r. And so we think, what is the time for this to happen? Well, if it does one revolution, we call that time the period t. And so if I solve for v center of mass, I get 2 pi over period t times r, which is just another way to write omega times r. Remember that omega, the definition is 2 pi times the frequency, which can also be written as 2 pi over the period. So that's one way to think about it. Another way is to combine the two motions. So we have our translational motion and our rotational motion. And so let's assume that the translation is going at the speed v center of mass as we talk about. And then over here, we'll assume that the rotation is going with this new equation, v center of mass equals r times omega. And so if just the rotation part of the disk, the center of the disk is not spinning, and then the top part is moving to the right, and the bottom part is moving to the left. If we add up the speeds, so for the top one, I get v center of mass plus v center of mass, that gives me 2 v center of masses. So the top of the disk is moving very fast. For the middle, I take the velocity of the center of mass plus a 0. That gives me just the velocity of the center of mass. And finally at the bottom, which is kind of the important one, we get velocity of center of mass and then negative velocity of center of mass. So those cancel, and so at the bottom we get that the velocity is 0. This is kind of a hard thing to get, but really this is the definition of rolling without slipping. There is no relative motion between the wheel and the ground, so the velocity is 0. And in order for that to happen, you have to have that relationship. The velocity of a center of mass equals omega times r. Okay, that has to be true with rolling without slipping. So the big key is we can use this viewer equation anytime that we hear rolling without slipping. So as an example of how this can help us, let's say we have a solid disk rolling down the road with some velocity. We want to try to represent its kinetic energy. Now we know we have to have 2 pieces, the translational and the rotational. But what we can do now is, because we know this relationship here between the angular velocity and the linear velocity, so I know omega equals v over r, so I'll call it big R. And here we're going to drop the center of mass motion just to make life a little bit easier, so we're not having so many things to write. And then if you look up in the book, the moment of inertia for a solid disk is 1/2 mr squared. So here's my equation. And what I do is, for the second term, which is the more complicated one, I plug some things in. So here I plug in the moment of inertia, and then here I plug in this guy, omega equals v over r. Since omega is squared, it'll be v squared over r squared. A couple things happen. First of all, the r squareds cancel. And so the kinetic energy, when you write it out this way in terms of the velocity of the center of mass, does not depend on the radius of the object. And then what we do is get 1/2 times 1/2. Remember, this 1/2 comes from the moment of inertia. It represents how the mass is distributed in our object. And so I get a total of 1/2 mv squared plus 1/4 mv squared. Altogether, I get 3/4 mv squared, where of course 3/4 is bigger than our normal 1/2. So because this is rolling as well as moving translationally, there'll be a larger kinetic energy. But it's much easier for us to write it all out like this than to have these two terms here. So let's try this together. So here's one. So now we're doing the same kind of thing. I have a hollow cylinder now, and I want to know is if I know its velocity of its center of mass v, how can I represent its kinetic energy in just one term? So give this a go, pause this, and we'll talk about it in a little bit. Okay, hopefully you got D. If you look this up in our book, the moment of inertia is mr squared without any fraction in front of it. The fraction would be 1 maybe if you want to think about it that way. And so here when I write this out, again the r squareds cancel, and I have 1/2 plus 1/2, and so it's mv. Alright, and what you can do, and we'll do this in class, is you can do problems where now, just like we did in chapters 10 and 11, you can do energy conservation of mechanical energy, and using this as your kinetic energy. And it makes life much easier when you write it as one term instead of these two terms together.